So what I'm going to show in this short video is an enhanced model of the retirement planning. And this spreadsheet, if you look at it, I've got several cells in yellow. These are the ones you would sort of input for an individual's different circumstances. How old they are, what their current salary is, what their employer matches, and the retirement age, and their gender. You'll see where gender comes in a minute. So either M or F for their gender. The gray cells represent uncertainty. So if you look at the annual raise here, I have put into cells minimum, a mode most likely, and a maximum value, and the actual cell is a PERC distribution ranging from 0 to 3%, with the most likely thing being 1%. The employee contribution, this one I actually set up something called a sim table because the key decision variable you have, there are several, as I talked about in the previous video. Retirement age could be a decision variable, but your key decision variable that you do have control over, how much of your salary do you want to put into your retirement fund? So that's a key decision. And instead of running this model for one value, what I've done is put in a function called the risk sim table. Risk means it's an at-risk function. And the sim table merely tells the computer that instead of using a single employee contribution, use the values that range what's shown in column G, which is from 5% to 15%. And we'll see how the sim table, there's a couple of settings you need in order to use the sim table. So this cell's just saying, don't use a single value for the contribution. Have it range from whatever cells G2 to G12 show. The rate of return is a normal distribution, but actually this cell is not going to be used. It's just there in a sense for comparison with the other model, because I've put it in column D as I did previously. The only difference here, instead of numbers, I use cell addresses. So I did put a mean and a standard deviation. And the mean and the standard deviation actually come from looking at the Standard & Poor 500. The actual mean, so over the whole time period, this goes from, these are adjusted for inflation, S&P 500 real rate of return from 1872 to 2017. Over that whole time period, the average was 8.46%. The standard deviation was about 18%. But I'm not sure that that's really sort of the best use to make of that historical information, because those early time periods were, you know, electricity was sort of first invented and rolled out, telephone service, huge technological improvements, plus the United States became a much more robust economy. There's a lot of growth years. I think focusing on the recent history might be better, so I'm going to actually just look at 2000 and 2017. The real rate of growth on average was 4.7% in the S&P 500, and the standard deviation was 17.5%. So those are the numbers that I put in right here is the mean and standard deviation. And all of the annual return cells are risk normal distributions using those input cells. And even though it's the same formula, it will be a different random draw. As you can see here, what's shown is each of those years, a different amount is being shown as the rate of return. I also identified 3 output cells. The year funds run out, just like it was in the original model. I also have an age at death. So actually what I did over here to enhance this model is I put in the actual life tables. So for males and females, this is the conditional probability of death in each year. So the way you interpret this is if you live to 7 years, if you live to 6 years old, the probability that a male will die before they reach the age of 7 is 0.000139. And it's a little bit lower if it's a female. when you get down here near the bottom of this, if you live to age 99, the probability a male will die by age 100 is now at 35%. If a woman lived to age 99, the probability they'll die before they get to 100 is just under 30%. And so that's, you notice actually they become fairly equal when you get to 118 or 119, which very few people. The oldest living person right now, I think, is 116. And there's about a 75% chance that they won't live to their next birthday. So these are the life tables, actuarially determined. And so what I did here is I have a column that says dead, question mark. What kind of distribution? It's a Bernoulli distribution. If you actually look up what, well, let me just do it in a different cell. What does the Bernoulli distribution look like? It's a discrete distribution. The Bernoulli distribution has two values, 0 and 1, and just depends on a probability. And so if the probability was, 75%, 75% of the time you get a 1, 25% of the time you get a 0, and the probability is only 0.001, almost 100% chance of a 0 and very little chance of getting a 1. So the way I put this into the model here is for each of these years, we use a Bernoulli distribution. What is the probability? The probability is on a lookup table. What you do is you look up the age, A15, so you look up the person's age, you look it up in this table. The way VLOOKUP works is, look, what value do you want to look up? Show the whole range for the table, which is Q4 to S, Q4 to S, whatever that is at the end, S123. And the first column of the VLOOKUP table has to be matched what you're looking for. So it's ages, you need the first column to be ages. And then you say, what column do you want to look at? And in this case, it depends on what the age is. So if it's the sexes, if it's male, you want to look at the second column of this table. It's the 2. If it's female, you're going to look at the third column of this table. And false just says, are you looking for an exact match or an approximate match? We're looking for an exact match. So each age, we want to look at this table, go down to the row for that age. So in fact, this very first one right now is looking at age 30. So it's actually going down to here, looking at this part of the table. And if it's a male, which I had it set on, it's going to basically take this probability, 0.0014. If it's a female, it's going to take the second probability, which is a bit lower than that. So what this column N is going to show is for each year, was the person dead or not? And actually, when you go down, you'll notice it changes. The formula is a little more complicated. The first one is just the Bernoulli. When you get to the second year of this, it basically says if the maximum of the prior rows in that column is a 0, then you look up the probability. Otherwise, it's 0. So once you die, and what's shown right here, right now, here's the first one that appears at this age, which is on row 35. At age 50, this person actually, we simulated them dying at age 50. And if they died at age 50, then we just want to identify the year of death. So if we just use the risk-Bernoulli distribution, it will keep simulating whether you can't die more than once. So it would simulate you might die at age 50, you might die again at age 60. In order to this be the only age of death, that's what the part of the formula that uses the max. If it's equal to 0, then you want to know, simulate, does the person die at this age? Otherwise, they've already died, because as long as the maximum is not 0, it means you already died before then, and you can't die again. So rather than saying dead question mark, think this would actually be the age at death. It's actually only one will appear in this column, and that's the actual age at which it simulates you dying. So then I have several additional things I'm going to calculate. Here's the age at death. All you do is have to look at that column N and count how many of the cells were equal to 0 and then add 1 to it. Let me make sure that N15. Just hold on a second here. Okay, I actually found a mistake in my formula, not unusual, as I was talking it through, so I'll show you what I changed here a little bit. Since N only identifies the age at death, I relabeled it age at death and added a new column saying, are you dead or not? And for this, I used the formula, if the maximum of N up to that row is 0, then make it 0, you're not dead, otherwise make it a 1. So you notice here, right now, what's showing is a simulated age of death of 63. And column N shows 1 there, but then 0 after, whereas column O shows 1s from there on that down because the maximum was not a 0, it was now a 1. So now I can look at column O and just say, I want to know how many zeros there are in there. Because once you're dead, it'll always be a 1. So I want to count up these zeros and I want to add it to your initial age. And that's why age of death says take your initial age and add up the number of zeros that appear in that column O. That'll give me the age at death. Now I have 2 output cells I defined. The reason they're in gray is because I added output to there, and so you see risk output in that formula. And the first is to compare the year that funds run out with the age of death. And if you run out before you die, then I may have to change the labeling on this. Let's see, right now you died at 63, and the funds would have lasted until age 70. So when you died, you still had funds available. So they lasted until you died. Because to me, that's actually the single best measure for me personally to think about looking at a retirement fund. It's not the only measure. You might just be in, well, I'll show you another one. But the first and foremost, what I'm interested in is, am I going to have retirement funds when I die? Because the worst case scenario to me is I run out of money before I die, which means I go on Medicaid and welfare and who knows what else, or become a burden for my son. The other thing I'd be interested in is when I die, how much fund is there? How much am I passing on to my estate? And so I also have here the fund at death. We use a VLOOKUP table. What we're going to look up is that age of death. We're going to look it up in the body of this table, which is A15 to K85. So that's through the fund at the end of the year down at the bottom. Going to look up that age. And next to the age that we died, we're going to pick up the 11th column, which will be the fund at the end of the year. So tell us the fund at death. So now I can simulate both when you die, simulate or pull out of that simulation whether it lasts, whether your fund lasts until your death, and what the size of the fund is at the death. In fact, just to see how this works, we've got the dice button pressed. Let's press F9, see what a couple of these values look like. So here's one where you fund lasts until you're age 74, but you lived until 90. The fund did not last until you died, and notice the fund at your death is a negative amount. Anytime it's a negative amount, it means you ran out of money. So, you know, maybe we could put in an if statement and make that 0 if we want. Doesn't really matter how negative it is, I suppose. Well, it might indicate you somehow your children have to borrow money to try to keep you going until age 90. Press F9 again. There's another one where you didn't last, you lasted until 99 years. Again, you ran out before you died. Now, your fund lasted until 101, you died at 88, and you've got a nice estate there at the end, you're over $1 million. Again, it didn't last, does last. You died at 64, fund lasted until 68, and when you died at 64, you had 171,000. So this seems to be working, this model. Now, I also collected some additional information up here because I want to know what happens at different contribution rates. So what I'm going to ask for in here is I'm going to calculate a bunch of things after the simulation is run. So when you look at the at-risk functions, there are a bunch of functions for simulation results. At the end of the simulation, you can find out the mean, confidence intervals, correlations. The most common things are to want to look at the mean, maybe a standard deviation. You could be interested in the maximum from the simulation, or a certain percentile. Where's the 10th percentile of the simulation? Or a risk target says, what is the percent, what percent of the time will this number be greater than or less than some value? So I've used a number of these here. If you look at this table, the mean, the year runs out, each of these is a risk mean function. I want to know the mean of cell C11, which is the year fund runs out. Then I have a comma F2, and that's where I put the simulation number here, because the other thing we're going to do, once we put the employee contribution as a sim table, I now want to tell at risk to calculate the mean that year runs out with a 5% contribution in the first simulation it's going to run. I'm going to actually tell it, and you can see it up here, I told it to run 11 simulations, one for each of these contribution levels. So the first simulation, it will use a contribution level of 5%, and I'm saying calculate the mean that the mean year that funds run out from the simulations using the 5% contribution level. That's where the comma F2, first simulation, comes in. Then I'm going to do it for the second simulation, which means a 6% contribution level. Then I'm going to do it for the 7% contribution level, and so on. The second calculation I'm going to ask for is the probability it lasts to age 81. Risk target says, what is the probability that cell C11, which is the fund a year is run out, you want to compare it to age 81 for this first simulation and for the second simulation, and so on down that column. But risk target tells you the probability that the cell will be less than or equal to something. So if I want to know the probability it lasts to greater than age 81, I would take 1 minus that risk target level. One modification I didn't do here is if you change this to female, then you probably want to change the 81 to an 83. So I probably need another cell that depends on, instead of hardwiring the 81 in here, have that be a cell address, which depends on male or female. I'll leave that for you to do. It's just a little modification. Then, what is the probability it will last until we die? This is looking at the risk mean of this cell right here, D12. This is a 0-1 cell. So every simulation, it's either 0 or 1. If you take the mean of a bunch of zeros and a bunch of ones, you're getting the probability, the fraction of the time it was a 1. So that is actually the probability it will last until you die. And then the mean fund at death is just looking at the fund of death, but looking at the mean of those values. When we run the simulation here, we're going to run 10,000, but for each of these values, so we're actually going to run 111,000 simulations. Let me go ahead and get that started. So I did that by changing the simulation number to 11. And now by using the simulation number in each of these formulas, it's going to collect the information as it goes through each of these simulations. So 110,000 simulations should take it a little while to run. It does appear it'll take about 2 minutes. You can see the progress down in the bottom left. It's on the 5th simulation already. It's actually only going to take a minute longer, speeding up. It's running 10,000 for each of those employee contribution amounts. And you'll notice we're showing right now it's showing the when funds run out, and there always has a sort of big bar. There's some sizable, in this case, a 10% probability it will last until age 101. We'll look at that window here in a minute. Let's just look at the table of numbers here because I think they make sort of intuitive sense. The year funds run out, the more money you contribute, the later that average year is. So if you contribute 15% of your salary starting here at age 30, on average it will last till you're 88 and a half years old, on average. But there's a range, and we'll see what that looks like in a minute. The probability it lasts to your expected lifetime of 81, the more you contribute, the higher that percent gets. At this point, it's not terribly reassuring that at age, contributing 15% of your salary a year, there's only almost a 2/3 chance that it will last until your expected lifetime of age 81. I consider that sobering, I would say. The probability it lasts until you die gets higher the more you contribute, but at 5% contribution, it's a little less than a 50% chance. At a 15% contribution, it only goes up to 73%. So there's still a 1/4 chance, greater than a 1/4 chance that you will run out of money before you die, even contributing 15% a year. And here's the average size of your fund at death. And the more you contribute, the bigger that is. It goes over $1 million at the 15%. You get a little more information here by trying to look at something like if you go to a summary trend chart, it wants to know what cell you want to use. And let's just say it's the, let's do the fund at size of death. It pops up a window here because it knows it ran 11 simulations. Which do you want to look at? Let's look at them all. And instead of this trend chart, I think box plots would be more revealing. So here's the range from showing 90% confidence intervals, and you can change that if you want. Or actually it's showing, I think the first percent to the 99th percent is actually what's being shown here. So no, it's showing 5% to 95%. You could change that. So these are 90% confidence intervals, and the middle box is the middle 50% of the simulations, as your contribution level goes up from 5% to 15%. And you can see that they shift upward. The 50%, the mean line gets higher. That's already what we saw the numbers in the table from. But now you can see the middle 50% is gradually getting bigger and bigger. The 90% confidence interval is getting bigger and bigger. And something that would not have been obvious, but comes off this chart pretty obviously, is you'll notice the range is getting wider and wider. So as you contribute more and more money, the range of possibilities is not just the average and the middle 50% that's getting higher, but the uncertainty about how big your fund will be at retirement is getting bigger and bigger as you contribute more and more. So there's an increasing range or more uncertainty at the higher contribution levels than at the lower contribution levels. We could try to see about a different chart here. That's the funded death, or about the probability it lasts until death. Let's see if we can get a picture that would look reasonable. Probability, all simulations. Yeah, it's not, it'd be better to just graph that probability column, which essentially is what this middle line is, the mean going from 46% up to 73%, which is what's in column J behind here. So the picture is not very useful. In fact, it would be better just to probably, graph something like those two columns just using an Excel chart. So, something like that. So this model has got quite a lot built into it, and again, to me, I find this kind of sobering. It's investment advisors usually don't do this kind of modeling. They usually make a single assumption about the rate of return. They don't let it vary from year to year, which is really the essence of what you want to do, because the rate of return is not just highly uncertain, it's going to vary each year. And the earlier you start retirement, of course, the more chance you have to things even out. That there are going to be some bad years, but they're going to be more than compensated by the good years. I find it somewhat sobering, though, that these percents here are not higher than they are, given the circumstances we put here. It's not a bad starting salary. We've got raises that are going to continue to go over time. And when you're contributing 15% of your salary to your retirement fund, that's quite a large, contribution, and the employer's matching 7% of your salary. I consider this fairly good circumstances. Not ideal, but certainly look pretty good to me, and it still shows, even with 15% contribution, that you're running substantial risks here. So then this becomes, I think, input to then saying, okay, well, maybe there's some other things we change. Maybe I shouldn't retire at 65. Maybe we retire at age 67 and see what that does. I'll just run one more just to see. If we change the retirement age to 67 and we rerun this, it ran pretty quick, so I think we can go ahead and run another one. Remember, the numbers were for 15% contribution, 73% chance that it would last until you die. So let's see how much higher we can get that number by pushing our retirement age back from 65 to 67. %, so went from 73 to 79% by waiting 2 more years to retirement. There are more tools in here that I may come back and make some other videos for, but you could pose a question like, well, just what do I have to do to retirement age, or some combination of these things to get the probability up to 90%, let's say, that it will last until I die. If that's your objective, to get that to 90%, can I do that with some of these levers? And you can answer some of those questions with additional tools that are built into at-risk. But this is a fairly detailed simulation model. I think for me, it goes well beyond things I've seen publicly available, tools that are given to the public. In fact, most investment brokers sort of are relying on sort of models that were built that you never see the model, and sometimes if you ask, you can get to see some of the assumptions they built in. The assumptions they build into those models, by and large, are, I think, less valid than what we're showing here. For the biggest problem being the rate of return. Most of those retirement models actually just assume a single rate of return and don't actually let it vary year to year. And that, to me, would be a major issue, because much more realistic when you let it vary. They tend to be more detailed when it comes to some of the demographic information. So they may actually estimate your retirement living expenses rather than using a single number, base it on a number of questions that they ask you. Anyway, I think this is a good example of what simulation modeling does, that how it works and what kind of probabilistic information it gives you. So I'll stop this video here.